Okay, it's time to learn some basic Verilog syntax. I think you have learned how to use module and end module. Okay, to define the scope of a function module, a function block. To make there is some function in this module, you have to declare signals. In Verilog, there is usually two different types of signals. That is late type and variable type. The keyword wire is used for late type, while the keyword rig is used for variable type. Okay, let me show you some example. For example, here we define this signal as wire late type, and the signal AB as rig variable type. After the declare of signals, you have to assign value to these signals. So in Verilog, there is also two types of value assignment. One is continuous assignment. You use this keyword of assign. Please say this example. You use the keyword assign, then followed by a statement. So the value of A and B will be assigned to the signal Y. This is called continuous assignment. And the other type of assignment is procedural assignment. That is assignment written in the procedural block. There is only two types of procedural block. The initial block we have seen before, and the always block. The always block will be introduced later. So this assignment, this are procedural assignment. Okay, so now you can declare signals inside the module and assign value to the signal. And there is some rule for different type of variable, different type of signals. For the late type signal, you can just use it in this situation, such as used in it as the left hand of assignment, and you can use it to collect the output of a module instance. Okay, let me give you an example. Okay, this is the module C and this is the module instance. You just put its name here and give it a instance name. This is instance name. Then and collected these signals. Collected this signal inside this module with signals at upper level. So at this point we use Y top at upper level to collect this output signal Y inside this module of this module. So Y type must be late type signal. Late type. Here we define it as wire. And also, late type signal can drive the input of a module instance. So, for example, A here and upper level, you can define it as late type. You can define it. Okay, this is the three usage of late type signals. For variable type, such as rig, it usually has two types of usage. That is used as a left hand of procedural assignment. That is left hand of procedural assignment and drive the input of module instance. So for here, AB is defined as variable type, and they can drive the input of this module instance. So this is the constraint of the usage constraint of different type of signals. So here you can't define it as rig type. If you write so, it will give you a syntax error when the code is compiled. And here you can't define it as a var type. If so, you will get syntax error. Okay, and here for while top, you can define it as rig type. If so, you will get a syntax error. Okay, this is the usage constraint for these data types. Please note that all the assignment begin with assign keywords. We call it continuous assignment. All the assignment made in the procedural blocks, that is initial block or always block, we call it procedural assignment. For procedural assignment, there is no keywords before it. Okay, this is the basic syntax you need to remember. But don't be worried. If you misuse something, you just get a syntax error and compile. So you just fix it and recompile again. Okay, let's use the basic syntax to define the function of an AND gate. So you have the module name, and give a name for this module. Then put the input and output signals here, and declare the detail of these signals with data type and the directions. Okay, for the module IOs, you have to define the direction of each signal, such as input, output. So direction, data type, and signal name. And within this round brackets, you list all the I/O signals. There is a comment after each signal, but there is no comment for the last signal. Then you write a continuous assignment to give the A and B value to Y. This is the function of this module. So this module is done. Usually when you code this module, you need to write this in a file. Yes, you have to write it in a file, and usually the file name and the module name is the same. This is too easy to find where the module is defined. Okay, let's see the key components inside this module. Now, you have defined a module, and you may want to simulate it. Yes, you may want to simulate it. That is, you give some stimulus at the input and monitor the output of this module. So this slide will show you how to simulate a module or a DUT, design under test. To simulate a module, you have to write another module. Okay. So you have write another module and instance the module you want to simulate. So this is the top level module. Top level. This is the sub level module. Or we can say this TB underline and is an upper hierarchy. So how to instance a module? The method is you list the module name here and give him an instance name. Then use a round brackets to collect all the signals. So the signal here, there is a dot precede here, the signal name. It means collected this signal inside this module. Collect the ABY signal inside this module. And how to collect it? How collect to which signal and upper levels? So this is the signal and upper level here. Yes, this is the signal and upper level. So the mean of this A and this A is totally different. So you can have a try. You can modify the Y name as Y top and collect it here. This is okay. That is, so that means using the Y top and upper level to collect the Y output of C add. Also, there is no comment for the last signal. Okay, so you have the top level module and sub module instance. Then you will try to give stimulus that is drive the input signals. So how to do it? You can define the internal signals. Yeah, define the internal signals and assign value to the signal A and B, like that. So you must know the meaning of this slide. So how about the meaning of this? This means wait a delay of 10 simulation unit. This is the meaning of this syntax. This is the keyword. Okay, this is a keyword followed by a number. So units. So what's the time for 10? 10 seconds, 10 nanoseconds, 10 hours, 10 minutes. So to define the time units, you have to use the keyword before a module, that is time scale. Okay, there is a symbol before it. Please note this symbol. This is the symbol at your upper left of your keyboard. Okay, time scale. So this time scale will define what's the time for unit. For this example, this is the unit. So unit. Okay, this, yeah, 1 nanosecond is the unit. So for this statement, it will delay for 10 nanosecond. And the 100 picosecond is the precision. What does it mean? It means if you write something like that, how many number of fractions the simulation tool will maintain, will keep. This statement, it means the simulation tool will just keep the precise of 100 picosecond. So for this statement, actually you may want 1 nanosecond plus picosecond, yes, but if you define this, it just has a precise of 100 picosecond, so it will give you the real delay of plus, yes, it will give you delay of this 10 nanosecond and 100 picosecond. So this is, so if you write this, they are the same, you will get the same delay. Okay. And if you write, yeah, you may get, sorry, so you may get, I suppose it will round up. Okay, it will round up. Okay, I'm not sure, but I suppose you may get the 10.2 nanosecond delay. Okay. So this is a simple explain of time scale and how to use it. The most important usage is to define the time unit for the delay statement. A delay statement begins with a symbol like that. Okay. So for all these statements, you have know how to use it. And for the last two, this statement we have explained before, and this is also a system function. Okay, finish. It tells the simulation tool when you execute this statement, the whole simulation will finish. You can exit the simulation program. So if you don't write this statement here, the simulation tool may continuously run this program, and it can't exit. So this computer may halt at this point. So for every Verilog program, make sure there is a finish statement that can be executed to make the simulation program exit from the simulation status. Okay, that's all for the test bench. Okay, usually we call this the test bench, and we call this the design under test (DUT). And the module show here gives you a diagram of that DUT, upper level test bench, and drive the input signals, monitor the output signals. Okay, let's compile and see how this code will work. Usually I will give 3 directories for them. This is the under Q. Okay, you can say this is the file, this is this file, and the pattern. I usually put all the DUT here. That is, the design will be synthesized to get level netlist, and this simulation pattern. I always put all the simulation pattern and this directory. Then another directory for simulation. Okay, we have file list and the make file. Okay, this is the file list. You just list all the file here, and this is a simple make file. Then open your Ubuntu system, okay, and change to the directory. Make sure the path to the file you write in your file list. Then you just let's remove the old files. Okay, there is just file list make file. Okay. Oh, sorry. One more thing in this file. One more thing. Okay, I haven't explained this before. This is the initial block to dump waveform. That is to save waveform for the simulation. The two are system calls. Okay, the two are system functions. This function is tell the tool the name of the waveform file. This is the name of the waveform file, and this tell the tool which hierarchy will be dumped, will be saved. For example, this line tells the tool this hierarchy from TB underline add. You should save the waveform, and this is defining the depth. If you give 0, that is all the submodules under TB add will be saved. Okay, so you give 0 is okay, and if you give it 1, that it says only the signal under TB is dumped, is saved, and the signal inside this instance will not be saved. And if you change it to 2, okay, that means 2 hierarchy, this hierarchy and 1 hierarchy under, so the signal inside this module will be saved. This is the usage. You need just write 0 is okay. Okay. Oh, let's go. Let's compile it. Just make theme. We will compile it. So after some time, it will done, and it will display the word here. This is what we have written in the code. Yes, and it will tell you that the simulation terminated because it has executed the finished task and to this file and to this line. Yes. 26. Yes, 26. Okay. So after the execution, you can see there is a file generated by compiler, and this is a waveform. Okay, this is a waveform file. We have defined it here. Yeah. Then we can use GTK wave to open the file. And give the file name. Oh. So you can say this is the terminal for GTK wave, and and this is a hierarchy of our design. You can see there is some signal names at this hierarchy, and there is a signal names in this instance. So you can select these signals and click append. Okay. And you can zoom. Okay. If you don't want to see this blue light, you can choose no grid. Okay. So you can see this is a waveform, and you can check it with our code. From the beginning, the initial, the same time in, AB is 0, and after 10 nanosecond, A is 1, B is still 0, and after 10, change. Yes, and after 10, finish. And Y is the output of this module. It's the function of AND. That's correct. Okay. So if you have add some signals, you may save it. You may save it and give it a name. This is a directory. You may give it a name. So you can say this is a waveform format name. Then when you reopen it, when you reopen this waveform, you can reload the saved file. Okay, so the signal will be here automatically. So this will, if there is a lot of signals, this will save you a lot of time. Okay, that's all for the demo. Okay, that's all for the demo. So here you will learn how to instance a module, how to give stimulus, a simple stimulus inside a initial block. Well, do you have any question about this simulation waveform? Do you have any question? For example, you just have one line here, but it seems that it has been executed several times. One time, second time, third time. Yes? Why? Why one statement can be executed for many times? If you have the programming experience of C or Perl, Python, you may think this is something impossible. Yes, one statement in this language always execute one time. So this is the nature of Verilog language. Okay, we call it we call it a event triggered language. That is, the statement is always waiting for the trigger. They are waiting for the trigger. If the trigger signal is triggered, this statement will be executed. So for this statement, the trigger signal is the input signal, that is A and B. Once A and B is changed, the value of A and B is changed, this statement will be triggered and will be executed to evaluate the value of Y. So that's why you may see from the waveform, anytime the value of AB is changed, the value of Y will be evaluated again. So this is coded. So this is the nature of Verilog language, coded event trigger language. Okay, let's see all the operators can be used in Verilog. I think you may be familiar with most of them if you have some programming experience. For example, you must be familiar with this, okay? And this. And this. And this. Yes. Most of them. Just take a look at. I will explain these remaining of them in later sections. Okay, this is the exercise 10. Can you write a Verilog code to describe all the combination logics you have known, such as OR, inverter, exclusion OR, mux, AND, and multiplier, even divider, using the operators here: AND, OR, exclusion OR, AND, multiplier, divider, subtract. Yeah. So can you write a Verilog module to include all the operations? You can define many signals inside the module, or you can define many output signals, and write a test bench to give some stimulus to the input of the DUT. Then instance the DUT in test bench and run it up in verilator and check the waveform in GTK wave. Okay, this is the exercise. So you can pause the video and do the exercise by yourself. And here I will show you the reference design. Okay, I will show you the reference design. So module name, I/O signal list, defining the I/O the direction and the data type of each signal. Then make value assignment to the output signals or the internal signals. Here we use continuous assignment. This is buffer. This is inverter and all exclusion OR, NAND low, not exclusion OR, mux. The meaning of this statement is If cell is evaluated to true, B will be assigned to Y marks, or A will be assigned to Y marks. So cell is evaluated to true means cell doesn't equal to 0. Okay. This is the under. This symbol you haven't seen it before. This is try to declare a signal of 2-bit width. If you don't use this, all these signals will be default as 1-bit width signal. So this is to declare a signal of 2-bit width. If you want to declare a signal of 8-bit width, you only use this format. Sorry. 7 down to 0. 32 bits width. Okay. To declare the function or to describe the function of marks, you can use assignment. You can use assign, continuous assignment, and you can also use procedure assignment. That is, you can define a signal with variable data type, use rig, then describe it, then assign the value to it in a always block. This is the always block. A always block, you need to begin with always, and then a ant symbol with a round brackets and begin end. So this is something the same as initial. Okay, within the begin end, you write your statements. This symbol means wait for the trigger of input signals to this always block. The input here is cell A, B. So when cell A or B is changed, this will trigger the execution of this always block. So this means wait the trigger. The trigger. The star here means all the input signals to this always block. That is all the signals you used in the right hand of assignment and in the conditional compare. Also, you can write it like that. You list all the signals here and separate them with all. So here you tell that the input trigger signal is cell A and cell A or B. Okay, we call the signal list here is as sensitive list. Okay, we call this sensitive list. That is, which signals are they always block sensitive to? And we prefer you write it in this format, so that the tool will automatically fill the sensitive signals for you. No need for you to list one by one. Okay, this coding style is preferred. Okay, the function of Y marks and Y marks 2 is the same. Okay. So when you have the code, you can write a test bench. You can write a test bench to give some stimulus to it. So define module name and declare internal signals. These are internal signals. Then instance the module and give it a module name. Give it an instance name. Then collect all these signals. These are the signals of this instance, and these are signals at higher and upper level. Okay, they are the same. These signals and these signals are the same. They are collected together. Then you can use initial block to assign value to each of these signals. Okay, that's all. Then you can go to the directory and run this simulation. Okay, I don't demo it. Okay, you can try it by yourself. Okay, by now, I think you have learned more than 20% of the most commonly used Verilog syntax. For detail of the syntax, you can refer to the standard. This is the standard of Verilog. I will show you. Yeah, this file. This file is the standard of Verilog. It defines all the syntax used in Verilog language. Okay, that's all for this section. In this section, you have learned how to describe combination logics using Verilog and how to generate simple stimulus to the DUT and how to simulate it under verilator and check the waveform in GTK wave. Please do the exercise. More practice, more progress. Thanks.